Hello, I'm Roberto, postdoc at the Stanford Vision and Learning Lab, and I'm going to talk about my research on interaction loops in robot perception, learning, and control. The current AI revolution has been strongly based on datasets, especially in computer vision. These large datasets sample the distribution of natural images and map a manifold that can be learned robustly in an offline manner. However, from a robotics perspective, these datasets fall short when it comes to learn to interact because they only contain static images and they are passive. A robot cannot learn how to interact with the environment from them. In robotics, we need to perceive, understand, and take decisions based on the state of the environment, which is usually an intractable distribution. Additionally, each new interaction of the robot will change the state. A robot as an interactive agent needs to understand and control the structure of the combined state-action space that changes dynamically, which is a non-stationary distribution. Classically, the solution to deal with this complex state-action distribution has been to limit interactions to reduce it to a quasi-stationary problem. For example, robot perception has been traditionally considered a passive procedure of sensor signal processing. Navigation in robotics usually means to reach a goal avoiding any interaction that could change the state of the world, and many solutions try to reduce interaction to the minimum necessary. In my research, I propose the opposite, to exploit physical interaction as much as possible to generate novel solutions. First, I develop a new solution for interactive perception. In interactive perception, the idea is to exploit physical interaction to perceive the world and obtain information that cannot be perceived passively usually. I apply this concept to the perception of articulated objects composed of links and joints, such as doors, cabinets, and drawers. To do that, I propose a solution of coupled recursive estimation loops that take a stream of sensor signals and interaction data and extract information using physical priors. I also exploited interactions to solve new navigation tasks. In interactive navigation, we move away from classical solutions that avoid interacting into a new type of navigation, more natural, where interactions are an intrinsic part of the solutions, for example, to push obstacles away or open doors. We develop a novel hierarchical reinforcement learning approach where the high level can decide on the part of the environment to use, the base to navigate, the arm to manipulate, or the combination. With this solution, we train visuomotor agents that interact with the environment to reach their desired destination, for example, opening doors. Finally, I also studied how to learn to interact better in contact-rich tasks, such as wiping a surface. What we did was to modify the classical reinforcement learning paradigm where the agent provides actions that are low-level robot commands by integrating an analytical controller that transforms the actions of the agents into low-level robot signals. In this way, the controller provides a new action space for the agent to learn. We propose variable impedance control in end-effector space, or VICEs, as a new action space for reinforcement learning, and we observed that for contact-rich tasks, the abilities provided by VICEs to control the interaction allows to reach the highest success rates and facilitates into-real transfer. All these projects share a common key insight. They leverage interaction to create new solutions. Thanks for watching and contact me for further questions.